I'm trying to make it very, kind of like show-like, as you can probably tell, and make it more exciting, because, I mean, chemistry can be a little dry sometimes, so I want to, make it more fun for you guys. So let me know how you guys enjoyed that intro. I want to say hi to everyone who is here in the chat. I can see we have Andres, hello, and we have, I think we had earlier was Leia, and then Ryan, hey guys, Miss is saying hello, I love you, thank you, and Krista Joy is saying hello, welcome, thank you so much for being here. I am so excited to show you guys this new live show that I have, the Ask Melissa Maribel live, and pretty much what this is all about and what we're going to be doing here, how this format is going to work, is this is a place where you guys will tweet me your chemistry questions before Sunday, before the next live, and then for a chance to get them answered on the next YouTube live stream. So that's what we're pretty much going to be doing here. I really picked questions that I got this past week from Twitter that you guys asked me. So I created a totally detailed lesson for the people who tweeted me. That's actually what I've been doing now, and that's how this format is going to work. So for everybody who put questions in the chat, so I'm doing it a little bit differently this time around. Of course, you are going to be able to get a chance to get questions later answered, not today specifically. Today we're focusing on dimensional analysis, stoichiometry, reaction stoichiometry, and limiting reactants. I have a detailed lesson that I made for the people who tweeted me on Twitter. So what I can actually do for everybody who posted things, I could always point you to the right direction. So I'm happy to send you guys to any videos that I have currently on those topics. Okay, so that's what we're going to be doing today, and I'll go over more of that as well. So another thing that I want to go into, let's actually start off with just the first topic on dimensional analysis. I got multiple people asking me for help with dimensional analysis, same with stoichiometry. So you'll see on there, there's also, there's actually tweets. So I will be showing you guys' tweets just so you can see who is asking, and I think it makes it kind of cool. So we'll be going over dimensional analysis, stoichiometry, reaction stoichiometry, and limiting reactants. And then for everyone who's going to be watching this later, so after the live stream, everyone watching the replay, I will place timestamps in the description box so you can instantly go to whatever subject you guys need help with. And as well as in the description box, you'll also find other helpful resources towards the bottom. Those are just other resources that I've personally used, that I recommend, and that I know can help you pass chemistry this semester. Okay, so why don't we go ahead and start with our first topic, which is dimensional analysis. And I want to start off with just how in the world can we set up these unit conversions, okay? So unit conversions I've seen to be a big problem, all right? So with the proper setup overall is going to be always aligning your units across from each other. So the main thing here, let's say if we only had one conversion factor, and remember a conversion factor allows you to go from one unit to a completely different unit, all right? So like let's say if we're going from inches to feet or from pounds to kilograms and so on. So the proper setup is that you're always going to see here is your given unit will always be aligned right across from each other so they can actually cancel out and get to the different unit, as I call it, so a completely different unit or whatever you're looking for. So essentially, you're always going to start off with the given unit. So let's say you're given feet and you're asked to get to inches, then the feet would be aligned, they'd cancel and go to inches. And the same sort of setup goes with something, let's say, with two conversion factors. So here you'll see, okay, we have two conversion factors, right? These are two conversion factors. And again, we'll have our given units across from each other. Those would cancel. And then our same unit now, so this is kind of like sort of a different unit. Like let's say if we had, now we're going from minutes to seconds or something like that, then those would cancel out. And I think you guys are starting to get the point where really it's just canceling out the units, putting them across from each other and going to the next step. So let's continue with this and let's see what else we have. So let's start off with the metric system. So the metric system, there's a trick for this if you guys aren't familiar with my trick. So what the trick is you're always going to place your base unit. So the base unit is going to be like grams, meters, liters. Those are your typical base units. And that's going to go with 10 to some sort of power, some sort of exponent. And so all of these, every single one of these is only going to go, so every single one of these is only going to go with grams, meters, or liters. Okay. So that's the general concept. And then what you're going to do, where the 1 goes, you're going to place the one with the different unit, or sometimes I like to think of it as the one with 2 letters. Okay, so the one with 2 letters, like let's say these are all the different symbols, all the different units. So you can think of it as, let's say if we had milligrams or centimeters or nanometers and so on. All of those would be placed with the 1. Okay, so let's actually do one. So let's say if we wanted to convert 50 grams to milligrams, what we need to identify first is what's our base unit, what is the different unit, and what conversion factor we're going to use based on the metric system. So our base unit is going to be grams. It's the one with the 1 letter, right? And then you'll also note that this part right here, that grams is present in milligrams. So that's how you know it's the base unit. They both share that in common. And then our different unit, as mentioned, is the one with 2 letters. So continuing on with that, now we'll see, okay, our conversion factor must be 10 to the negative third, because we saw that here, right? 10 to the negative third is right here. And then next, the 1 milligram, so 1 goes with that different unit. So then setting this up, I'll start off with our given unit, which is the 50 grams. And then I'm going to align the units of grams so they can cancel. And on top, place the different unit, right? So on top, place the different unit just so everything can cancel out and we'll be left with milligrams. So then our final answer would be this large number of milligrams. And another thing, by the way, you could have written this in scientific notation. It does depend on your teacher, your professor, what their preference is, but I typically see they like to have it in scientific notation. It's just, it's kind of like an easier way to write it, just because you don't have to have so many zeros. You don't have to worry about such large numbers or small numbers. So our scientific notation would be this. And how we would have done that is you would have grabbed here. So we would have moved this over 1, 2, and 3, actually. I think I put too many zeros on accident. I did. But this would have been 5.0 times 10 to the third. But that's how we would set this up. And then let's do another one. So let's go backwards now. So what this is helping you with, I know it's a little bit different from maybe what you guys were taught in class. The reason why I teach it this way is because I always see students ask, when do I multiply by 1,000? When do I divide by 1,000? And it can be a little bit tricky, and I would rather you just have one method that works for everything instead of, having to remember, oh, do I flip it? What do I do? So that's why I like to kind of show you this trick. This works every single time. So you don't have to keep remembering, when to flip it or whatnot. So we're going to convert 300 milligrams to grams. And then what we're going to use the same exact conversion factor. And we'll start off with our given, which is 300 milligrams. We want the milligrams to be on the bottom so that those can cancel. And then those milligrams would then cancel. So these milligrams will cancel, and then we'll be left with grams, since that's what we're looking for. So we'll be left with grams. And remember, this 10 to some sort of exponent always goes with our base unit. That would cancel, and we would be left with 0.3 grams. Okay, let's do something a little bit, I'd say tougher, but not too much, okay? So what we're going to do is we're going to convert 450 nanometers to centimeters. So there is an additional step to this one. So we actually need 2 conversion factors. The reason for this is because we're not just going from nanometers to meters or from meters to centimeters. Instead, we're going from a different unit, so nanometers, to, once again, another different unit, so centimeters. So instead, we need to identify our base unit. And how you'll be able to identify your base unit is right here. They both are hinting at it, right? They both have meters in the actual unit. So we know our base unit must be meters. So the middle step is to go from nanometers to meters and then to centimeters. All right, so that's what we're going to be doing first. Okay, identifying our conversion factors. Now, I want to show you a trick. You're going to go from nanometers to meters first, right? That's what we stated. That's what we stated right here. Now, whenever you're trying to convert to, or even identifying what your conversion factors are, you're always going to have your given unit, so nanometers, and then that's going to equal a different unit. And then the second conversion factor must equal that different unit, okay? So it had to have been meters because you want those to align and completely cancel out. So that's going to completely cancel out, and then we'll be left with our whatever we're looking for. So that would have been the centimeters. So that's going to be your hint right there, is just understanding, okay, my first conversion factor must equal at least part of the second conversion factor in order for those to cancel out. Okay, so let's set this up. We'll start off with our given, which is the 450 nanometers. We'll align the units of nanometers so they can cancel out. And then those now have canceled. We're at meters. And then next, we want to use our second conversion factor so those can cancel. And now those cancel. And finally, we're at the actual unit that we wanted, which was centimeters. Next, what you would do is you would actually just multiply straight across, and you'd get here. Let me show that. So you would multiply straight across, so you'd get 450 times 10 to the negative ninth, all divided by 10 to the negative second. Another little trick for you is if you were looking at, let's say, something like this. In going back to like math and these properties of exponents, what you would actually do is whenever your bases, so your bases here is 10, whenever you have those two being divided, you're actually subtracting the exponents. So this would have been negative 9 and then minus that negative 2. So that would have been negative 9, actually plus 2, so negative 7. So just in case you were to see that and need to understand what in the world's going on there. Okay, that's a little trick for you going back to algebra. Okay, so let's keep going. And now let's go back to more of dimensional analysis. And something to note, by the way, guys, is common conversion factors. So you will need to know the metric system. I would say definitely memorize that. And then the other thing that you'll need to know are common conversion factors. So if you haven't already, I actually made this a lot easier for you guys because you have enough to worry about. Actually, I can put in the chat right now, I can put the chemistry survival guide that I made, and that has both chemistry 1 and 2, and you'll find the common conversion factors that you'll need. You'll also find the metric system that you saw me use earlier. So all of that is in the chat right now. That is completely free. That is my gift to you to help you survive chemistry. All right, so let's try out this question, and we're going to use our common conversion factors, and we're asked to convert 0.890 quarts to milliliters. Okay, so here, this is what we're going to have to figure out. We have to figure out what conversion factor are we going to use? And I think that tends to be the hardest step sometimes because you don't know how to connect everything and then get to the final result. So what we're going to do is we're going to, let's see. So we're going to go to quarts to milliliters. Okay. So now quarts to milliliters, let's just start off with what we're given and then what we're finding. So what we're given is that 0.890 quarts. We're asked to find milliliters. Okay, so let's start off with our plan. We're going to start off with quarts, and then we're going to get to liters. And then how I was able to even figure that out was knowing right here, was seeing that, okay, I know that 1 liter is equal to 1.057 quarts. So that's something that I definitely have to use to then get to liters. And then now knowing your metric system, we can go from liters to milliliters. And that's actually the next conversion factor in the next step. So we'll go from liters to milliliters using our conversion factor. And then now we just have to set everything up like we did before. Okay, so, and then this is a little hint for you guys that I mentioned. 1 unit for your conversion factors will always equal the previous unit. And by that I mean this, where we have liters and liters equaling each other. Those have to cancel to get to what we actually wanted, which was milliliters. All right. So let's align everything right now, all of our units, so they can cancel. We'll start off with our given unit, which is quarts. Now, once again, we'll align those units, so quarts using our first conversion factor, and on top, we have 1 liter. Okay, so those would then cancel, and then now we want to get to our second conversion factor, so we'll put liters and liters across from each other, so those would cancel, and on top, we'll have 1 milliliter, which is exactly what we wanted. We wanted milliliters, and then, of course, we'd make sure when you're doing this, guys, that you multiply the bottom first, then divide. So then divide, 0.890 divided by the bottom multiplied. And then our final answer would be 842 milliliters. And then, of course, always knowing your sig fig rules, that's something major. I don't want you guys to lose any points for something, so small. So always start off with looking at your given. Our given has 3 sig figs, so that's why we rounded to 3 sig figs as our final answer. All right, so let's do one more of these, and then we'll move on to stoichiometry. And by the way, everything that you guys are seeing here, a lot of these questions I actually pulled from the notes that I make. So if you aren't familiar with notes that I'm making, so I like to make really detailed kind of like how-to guides for specific topics that I know are challenging, and I've already made those notes that I just put in the chat right now. So this is dimensional analysis. It also includes density, metric system, and sig figs. So all of that is packed into one. And I also have a promo code that I'm going to share right now to you guys. So a promo code that we're doing is back to school. So of course, right? So the promo code is back to school, and you get 25% off of the notes, of all notes, and that expires the 16th of this month. So make sure to check that out, to shop those notes. The notes, they are very, very beneficial. I've heard so many good comments from people who actually purchased them. It saved them time, and basically you don't have to worry about how complex your book is, because I explain everything that you need to know in the notes. Okay, so let's do an example from the notes. So here we have the healthcare provider writes an order for this crazy sodium, this crazy drug that we have here, okay? So 50 micrograms of PO-stat. Each tablet contains 0.05 milligrams. How many tablets would you administer? All right, let's start off with just figuring out what in the world we have. All right, so what we're given is 50 micrograms, and then we're asked to find tablets. So we actually were secretly given a conversion factor within the question. And a lot of times this might happen. This is kind of like a tablet question or a standard question that they normally give you on an exam, or if you're, wanting to be a nurse, this is a common question that you'll have. So what you're actually going to see here is they're saying each tablet, so that means 1 tablet is equal to 0.05 milligrams. And that's actually going to be a very, very important conversion factor that we'll use very soon. So that's going to come up. What we want to do first, though, is we want to go from micrograms to grams. And the reason for that is because we eventually want to get to milligrams. And that should make sense because this conversion factor just told us that, okay, we need milligrams to connect to tablets. So if we were to change micrograms to grams and then get to milligrams, that would then allow us to go to tablets. So that's exactly what we're going to do. The first conversion factor comes from the metric system, since it's micro to just grams. And then same thing goes for the other one. The metric system is also used since we're going from grams to milligrams. And lastly, the one that we actually were given was milligrams going to tablets. So that's our last conversion factor. Okay, and that one was given as I mentioned. You'll note again that this is 3 conversion factors, but if you look at the trick and you look at, okay, well, I have grams for my first conversion factor, so then my second conversion factor must have grams in it. And that's why we have grams in it, okay, because those have to cancel. And then next, we're going to see this again. And okay, if we want to find our third conversion factor and it ends in milligrams, then the next part has to equal milligrams so they can cancel, and so on. So that's how you're connecting everything together, and it just makes it so much easier. So let's put this all together. We'll start off with our given, which was the 50 micrograms. We'll align the units of micrograms so they can cancel. And then from here, so we have those just cancels. We're now at this step to go from grams to milligrams. And then next, we'll go from grams to milligrams by placing all of our conversion factors. Those again would cancel, and now we're at milligrams. And the last step is to convert it to tablets using our third conversion factor. Okay, so after we multiply everything out, these cancel, we're left at tablets. After we multiply everything out, we just get 1 tablet, and that would have been your final answer. So a lot of these questions just have to kind of deal with knowing your conversion factors and knowing how to align everything and piece things together. So I highly recommend you guys practicing more of these. And for that, I have made a playlist all on dimensional analysis to help you guys, further with this concept, which I'll put that in the chat right now. So if you're struggling with dimensional analysis, I highly recommend checking out the playlist and just, looking at those tips and tricks that I mentioned all throughout. So let's go ahead and now get to stoichiometry. For those of you who just joined, I know there might be a little bit of confusion. My previous lives, I would do, it was kind of like a free-for-all where everyone would just ask their questions and I would answer everything as much as possible, right? So instead, what we're doing, and the reason why I'm changing this format is just so everyone who's struggling with, let's say, all these different concepts, let's say stoichiometry, dimensional analysis, can come and actually watch this live stream and come with those types of questions. And then I will have everything be topic based now. So I just saw that it wasn't as beneficial as I talked to a lot of you guys actually, and I found that it wasn't as beneficial as I wanted. I always want to make this better and improve it. So how it's going to work throughout now is you guys will tweet me your chemistry questions throughout the week, so before the next live, so I can then pick questions to turn them into a custom lesson and detailed lesson. Okay, so and of course, just to let you know, I know I'm going to get a lot of questions, so I will be picking them for a chance to get them answered. So I can't say that I'm going to answer absolutely every single one. I'm going to try my best to answer pretty much how I chose this time around was I saw how many people were asking for stoichiometry. And actually, I had the most people asking for stoichiometry, so I knew I had to talk about stoichiometry. So if you want to get, a chance for your guys' question to be answered, I highly recommend telling your friends, telling your classmates to also tweet me, and I pick it on, what's the most common question that I keep getting over and over. Okay, so I hope that makes some more sense. Of course, at the end, I will see what other questions there are, and I'll see what resources I have as videos, and I'll do my best to put that in the chat as well. Okay, so let's move on to stoichiometry. And with stoichiometry, you're going to see that there's more conversion factors. So they all kind of go hand in hand. So what we're going to do here is there are 4 main conversion factors. And in my videos, you actually saw that I talked about 3. There's one more that you will later go into. I'll touch on it a little bit briefly, but pretty much what I want you guys to understand and know is if you know these 4 conversion factors, then stoichiometry is easy. It is a breeze, okay? And it's just because it revolves all around these 4 conversion factors. So I want you to think of it kind of like and it's like a puzzle, okay? Where let's say the first conversion factor asked you, or actually even the first question, the first puzzle asked you to go from grams to moles. And what are you going to do to actually put those 2 together or figure that out? Well, it's molar mass. And this is how the conversion factors are going to help you piece everything together and be able to answer the question pretty easily, Okay, so this is my trick to figure everything out. So our first conversion factor is molar mass. This allows us to go from grams to moles or vice versa, moles to grams. Next one is a mole to mole ratio. So a mole to mole ratio allows us to go from moles of one compound to moles of a different compound. You'll also see me even say moles of one molecule or a different molecule. What the difference there? A compound is typically talking about something that is ionic, meaning it's a metal and a non-metal, while a molecule is something that is covalent. Covalent meaning that there are two nonmetals. So that's going to be very, very beneficial and helpful to just know the differences later on. Same with naming. So that's going to be the concept with this. I also got a question on what in the world a mole is, right? I know that we get a lot of these questions, or like who came up with the mole? So what I want you to think of is kind of think of it like who in the world came up with measuring our weight in pounds, or in some places kilograms, who came up with putting our height in feet or inches, and so on. So these are it's just a unit of measure that we use, I'd say, for chemistry, for chemicals. So like moles is that sort of unit that we're able to just track for a specific molecule or a specific compound. So that's the general idea behind it. Okay, so I hope that makes some more sense to clarify what in the world a mole is. It's just a unit of measure, or really a unit that we can figure out how to measure that molecule or compound. Okay. So I hope that makes some more sense. Ryan just said, I'm an AP Chem and I still don't know what a mole is. I hope that clarified it. I hope that made some more sense. It's really just a unit of measure that we use for chemicals. Okay, that's kind of like the easiest way I can say it. So yeah, and then the next conversion factor, the third one, would be Avogadro's number. And from here, this one is going to equal 1 mole is equal to 6.022 times 10 to the 23rd, which we'll get to. And here we'll see that atoms, it's going to equal atoms, molecules, particles, or formula units. And it can go backwards. So back and forth, that's what it's going to be. Okay. So that's essentially the concept with Avogadro's number. You're just going from atoms, molecules, particles, all of these, and that equals 1 mole. All right, last one. So you guys will see this later on when you get to gas laws, where we're talking about liters at STP. STP is standard temperature and pressure. So that, to get a little bit into it, all that really means is gases are, if they behave ideally, I kind of want you to think of a gas as a 3-year-old. Okay. So if ideally they behave in these standard conditions or standard temperature and pressure. So ideally a 3-year-old will behave if maybe they're eating ice cream. So, or some sort of condition. Okay. So something like that. That's essentially what we're talking about. And moles are then equal to liters in this case. So, and we'll get into all the specifics, but this just allows us to go from there. Let me go back. All right. So this just allows us to go back and forth. These are the 4 different puzzle pieces or ways that we'll be able to figure this out. Okay. So knowing these is going to be extremely important. Let's get into it. Let's get into molar mass. And what molar mass even is, molar mass is the sum of each individual element's mass, and that's going to be found on your periodic table. So what we'll do here is let's actually find the molar mass of calcium nitrate. And what we're going to do first is we're just going to figure out the individual masses of each element that is in the compound. So what I highly recommend doing is what we're going to do is I'm just going to kind of like take out every single element that is within that compound. So we'll start off with calcium. That's going to be first. And then where I got that was the periodic table. So this is just a glimpse of what it would look like as you know, on the periodic table. You're going to see a number on the bottom. That's going to be the molar mass that I'm talking about, that I'm referring to each time. So that's 40.08. And then next, for nitrogen and oxygen, it's a tiny bit different. Because there's this 2 subscript on the outside of the parentheses, you actually have to distribute in that 2. So that's what it shows here. You're distributing that 2. and you actually have 2 times the mass of nitrogen. And then same thing with oxygen. You have 3 times 2, so we'll get 6, and we're going to multiply 6 times oxygen, okay? So all of this is going to be a little bit easier now that you understand, okay, I have to distribute that subscript in, and that's how we're getting 6 times the mass of oxygen. So once we do that, once we actually do all these values, we'll add them all together, which you'll see in step 2, and then you'll get the molar mass. So that's how you find the molar mass overall. It's going to be very, very important because we will see that a lot. Okay, now that that makes some more sense, and let me know, guys, if you have a question regarding this. And Ryan actually just did perfect. So molar mass question, how many sig figs should we go out to? So that's going to depend on your periodic table. So how I see it is your teacher's going to give you a periodic table to use. You're going to actually use, and by the way, periodic tables are different, unfortunately. So I use a different one. Your teacher probably might use either the same one or a different one. But what I want you to do is use the exact numbers that are on there. So like, let's say here I actually used, 40.08. So that's 4 sig figs. So everything had, and here this should have been 96.00. So everything has 4 sig figs. That's why I rounded to 4 sig figs. So it's dependent on the periodic table that you use. And then there you'll see, like, let's say if this molar mass initially was 5 sig figs, then you'd round to 5 sig figs at the end. Okay. All right. Let's move on to a different question. Using molar mass. Actually, this is a good example. So whenever we're trying to go from grams to moles, this is how the setup is going to be. So your setup is going to be where your grams are always going to start first, and then you want to cancel out the grams, so we'll align those units, and on top we'll have the moles. And then same goes now if we're going to kind of reverse this and go from moles to grams. So moles will then be aligned across from each other, so on the bottom, and then we'll get to grams. So this is just a quick little thing if you forget, oh, how do I align them? Where does everything go? And so on. All right, this next question. So how many grams are in 0.31 moles of calcium nitrate? All right, so what we want to do, as always, identify what we're given, so that's what we're starting with, and what we're finding. And then we'll see how in the world we're going to get to whatever we're finding. So we're actually going from moles to grams since we're given 0.31 moles of calcium nitrate, and we're asked to find grams of calcium nitrate. So the molar mass that we just found, was this amount, right? So we have that already. And by the way, if they didn't provide it to you, you have to figure it out using your periodic table. But now you know how. And then let's go ahead and set this all up. So we'll start off with our moles, which was 0.31. And then we're going to align those units. So on the bottom, we'll place 1 mole of calcium nitrate per every 164.1 grams. And let's make a note there. So whenever we're talking about molar mass, this grams per mole is essentially saying this. We actually have 164.1 grams, and that's equal to 1 mole. So that's always going to be the case. With molar mass, you will always have 1 mole. The only time where you start to change moles is a mole-to-mole ratio, which we'll talk about. But that's essentially the concept with molar mass. You're always going to have the grams going with the number, right? The number on top. So let's say 164. And that's going to equal 1 mole of whatever compound you're using. Okay? And then our final answer here, so those would cancel. Our final answer would then be 51. And then how I figured this out for sig figs was just the fact that initially we only had 2 sig figs. So I had to round to 2 sig figs. So that's how I knew the sig figs as well. All right. So I'm going to move on, actually, because I want to get to the next part. That was just another example. So mole-to-mole ratios. Okay. So mole-to-mole ratios, this allows us to go from moles of one compound to a completely different one. So moles of compound A to moles of compound B. Okay. So like moles of carbon monoxide to moles of oxygen. So it just allows us to kind of change it up a little bit, right? Change the compound, change the molecule in that case. So the next thing is just and vice versa. So the next thing is where to find a multiple ratio. So there's actually two different places where you can find a multiple ratio. One will be the coefficients that are found in your balanced equation. And always make sure that your equations are balanced. I have seen that as a trick on exams, by the way. Whenever you, like, let's say, goodness, I've seen this a lot actually. They'll give you an unbalanced equation and they expect you to know that you have to balance it, but they don't tell you. So beware of that. I would always make sure to see, is the equation balanced before you just jump on in. And then the coefficients that I'm talking about are the numbers that are in front of all of your elements or compounds or whatnot, okay? So those are the coefficients that I'm talking about. And then lastly, any subscripts that are found in your compound or molecule. So in this case, we're given a compound, and then what we would do is we'd actually look at I can't really show it there, but we'll actually look at the subscripts. So like, let's say oxygen has a 3 subscript, but really we know there's 6 of them, and we'll get into that in a second. But understanding that those are the 2 different places we can get a multiple ratio. Okay, so those 2, yeah, perfect. Okay, so let's say with this example, let me go back 1 sec. Okay, there we go. So going to this example where it's asking us how many moles of I2 are in 8.2.3 moles of sodium iodide. And then we're given the 8.23 moles, and then we're asked to find our moles of a totally different molecule or compound. So in this case, we're just going to use a multiple ratio. And how we're going to do this is we always start off with the given. And then now we want our moles of sodium iodide. We're going to align those across from each other. And where I'm taking those numbers, this 2 is going to come from our balanced equation. So that's where I'm taking this number right there, okay? And then here on top, that 1 is once again coming from that balanced equation that I found initially, or that was actually given to us initially. And then next, all we have to do is cancel those out, really just divide by 2. And our final answer is 4.12. You'll also note sig figs, that your sig figs here are just, 3, and that's why we rounded to 3 sig figs. Okay, so that's the idea there. Let me continue with this part. So if we were to figure out and we were asked how many moles of oxygen are in this entire compound of calcium nitrate, okay? Well, what I want you guys to notice is if we were to actually even think about how many moles of each element there are within, this goes back to understanding that this 2 subscript actually gets distributed. So here we see, okay, for one entire molecule, or one mole of calcium nitrate, we're only going to have 1 mole. Like, think of it as there's only 1 of that compound overall that we're initially given. So that's going to then equal 1 mole of calcium because there's no subscript here. And then next, we'll see that, okay, there's still, once again, 1 mole of calcium nitrate, and this is going to be 2 moles of nitrogen. Why? Because of this 2 subscript, because we had to distribute there. And then the same thing goes for this last part, where we're actually multiplying 3 times 2, and that's why we're getting this 6 here of oxygen. So I highly recommend knowing where those multiple ratios come from. Those are the 2 things: balanced equations, coefficients and balanced equations, and any subscripts we may have in just a compound or molecule overall. Okay, let's move on to Avogadro's number, where this is going to be Avogadro's number, so 6.022 times 10 to the 23rd. You may also see it as 6.02. That's acceptable as well. And then that number is always going to go with atoms, and that's going to equal 1 mole. So that Avogadro's number goes with atoms, particles, molecules, and formula units, and it all equals 1 mole. Okay, before I move on real quick, I think someone just said, I have a question about how to convert grams to minutes. Interesting. Elaborate. Let me know, was it minutes or moles? Because that's different. I might check that at the end. I'm going to keep going, but let me know, Andrea, that if whatever that was, going from grams to minutes. But I'll check that back at the end. Let's keep going with Avogadro's number. So once again, we can go from moles, that's moles, to atoms, particles, molecules, and formula units. And the setup would be something like this, where on top we'll have, the moles, those are going to cancel, and then what we're going to be left with are atoms, particles, molecules, formula units, and so on. Okay, so the next thing is if we were to reverse this, where this was atoms, particles, molecules, and then that in formula units, and that would go to moles, and the setup would look like this. So it's all about just knowing what in the world, how are we going to set this up? What conversion factor are we going to use? That is extremely important. So that's the idea here. So let's try one. If we were asked how many moles are in 1.023 molecules of carbon monoxide, and we were given 1.03 times 10 to the 23rd molecules. Now, whenever we're asked to go from molecules to moles, Avogadro's number, right? So Avogadro's number, that's going to be the main thing here, okay? So what I'm going to do is I'm going to start off with our given, and then on the bottom, Avogadro's number will be. And that's just because that has to go with molecules, atoms, particles, and formula units. And we're always aligning those units across from each other. So next, that'll give us moles. And then here, those would cancel out, and that would give us this amount of moles. And then lastly, we know how many sig figs to round to because this is 3. Okay, so 3 sig figs since we started off with 3 altogether. All right, so let's move on to liters at STP. Okay, so the main number that you're going to have to know for liters at STP. So liters at STP allows us to go from liters to moles. So that you're going to see this later on in let's say, gas laws. So gas laws is when you're going to see this, okay? So liters is equal to 1 mole. We'll see 22.4 liters is equal to 1 mole. That is going to be very important to know later on. And then moles allows us to get to liters. This is going to be your setup, and vice versa. So I think we're starting to maybe see that pattern where you're always aligning your units so they can cancel to get to what you actually want. Okay. So let's say if we had something like this, where it's asking us what volume will 0.0872 moles of CH4 occupy at STP. So that's going to be a key thing to note, that STP is that hint that you have to use the 22.4 liters is equal to 1 mole. Okay, so our given is that 0.0872 moles, and we're going from moles to liters. We'll start off with our moles, align the units across from each other so they can cancel. So that's why we have the 1 mole on the bottom. And then liters, that 22.4 liters on top, those would then cancel. And then we're going to be left with our answer. Now, with rounding here, we want to round to 3 sig figs. And the reason for that is because we have only 3 sig figs, because remember, leading zeros do not count. So that's why we rounded to 1.95 rather than leaving it as the actual initial one that we had here with a lot more digits. So that would be our answer. Okay. So, and Becca just said, probably a stupid question. No, nothing is here. Okay, I'm here for you guys. But what does STP stand for? Okay, standard temperature and pressure. So you guys haven't seen it just yet. Maybe some of you guys have, but you typically cover that in the section of gas laws. So you will see more of that there, but I still wanted to kind of make that clear because it will come back. And sometimes some people see it early for some reason. But yeah, standard temperature and pressure. And next, with reaction stoichiometry, this is putting everything together. So reaction stoichiometry is now going to be going from grams maybe to molecules, and we're having all of these conversion factors come together, which sometimes people fear, but that's why we're going over it, and that's why those 4 conversion factors make it so much easier to know, what do I do next, okay? So reaction stoichiometry, this first question says, how many molecules of oxygen are required to react with 174 grams of carbon monoxide? Okay, so, and they give you a balanced equation. How nice. Our given is going to be that 174 grams of carbon monoxide. and we're finding molecules. Okay, so this is where I want you guys to just kind of like stop and think. If we're going from grams to molecules, well, I know molecules only goes with Avogadro's number, right? That's it. That has to be it. So since molecules goes with Avogadro's number, what does Avogadro's number equal? Well, that equals moles. Okay, well, what does grams equal? What can I convert from grams to? Moles. So that's actually a hint for you. Every single one of the conversion factors that we talked about, the 4 of them, all equal moles. So it is safe to say that if you do not know where to convert, start with moles. Start with converting that first unit to moles, because all the other conversion factors equals moles, okay? So that's going to be something that's really, really helpful. A lot of times students don't know where to start, and I actually felt that way too in school. I would look at a question and say, what do I do? How do I start this off? And that's my hint to you. Start off with just converting to moles. So that's our first step. We'll convert from grams of carbon monoxide to moles of carbon monoxide. And how we're going to do that is by using our molar mass of carbon monoxide, because grams to moles use the molar mass. All right, so we'll do that. So we have 174 grams that we're starting off with. I'm going to align the molar mass across from each other, or actually the grams across from each other so they can cancel. Remember, molar mass is grams per every 1 mole. So that's 1 mole of carbon monoxide on top. Next, our second step, since we'll see we actually canceled out these grams and we're now at moles. Our next step is we want to get to moles of a completely different molecule here, okay? So a completely different molecule, that's going to be O2. So we're going from CO to O2. So what we have to do is use a mole to mole ratio if we want to change the molecules overall or the compound overall, okay? So what I'll do is let's go back to our balanced equation. And if we want to go from moles of carbon monoxide to moles of O2, we need a mole to mole ratio. So our moles of CO would be 2 moles of CO per every, or let's actually go back. So that equals how many moles of O2? Well, if there's no coefficient in front, assume that there's just a 1. So first, always make sure, is it balanced? I want you to check that first. And if it is, and there's nothing there, no coefficient needed, there's just a 1. Okay, so then this would equal 1 mole of O2. Okay. So I'll use a mole to mole ratio as stated, and this is where our mole to mole ratio will go. So I want to align those moles of carbon monoxide across so they can cancel, and now we're at moles of O2. All right. So then next, our last step, we're almost there. Now that we finally changed the molecule to what we actually want, right? We want O2 instead of CO. We want to get to molecules using Avogadro's number. And that's exactly what we're going to do here. We're going to use Avogadro's number, so the moles will be aligned so they can cancel. We now have molecules of O2, which is what we wanted initially. And then, of course, what I recommend doing is I personally like to multiply straight across. So do that first, then divide by the bottom multiplied, and then that will give us our final answer of this value. And then note that your sig figs, what you would have is we initially started with 3 sig figs, so we have to end with 3 sig figs. Okay, so that would be it for that sort of concept of reaction stoichiometry. Now, this next one that I'm doing is actually still reaction stoichiometry because it's involving going from grams of one reactant to grams of product, or so really think of it as grams of, let's say, one compound to grams of a completely different compound. So limiting reactants is still stoichiometry. Okay, so what I just put in the chat, by the way, guys, is the link to my stoichiometry notes overall. All right. So that will help you out for sure. I just saw a question of for Rachel. Oh, thank you, Becca, for answering it. Perfect. Thank you. Thanks, guys. Yeah, I love that you guys could also, now that you're learning too, right? You guys could also answer these questions, which is awesome. It's an awesome feeling to be able to answer other questions and actually feel like I got this. I actually know this stuff. So great. Thank you. For limiting reactants, now let's go into limiting reactants. What you're going to see is we always want to go from grams of reactants to grams of products. And that's going to happen twice. Okay. So pretty much, and actually even before going into this, Krista Joy just asked, so depending upon what the question is asking for reaction stoichiometry, for the final step, you would put Avogadro's number, grams per mole, etc. Exactly. Okay. So that's why it makes it so much easier to understand like the 4 different types of conversion factors, because that automatically tells you how am I going to piece everything together based on what the question is asking. Right. So then that's why we ended with Avogadro's number, because the question asked for molecules. And the only thing that has, molecules with it is Avogadro's number. Right. So yeah, like understanding that connection is what's going to be so simple once you figure that out. Okay. It's going to make it a lot easier. Okay. So let's go to limiting reactants, and then we'll see what other questions you guys have. And all right. So limiting reactants here. Okay, so let's say if we're given this amount, 167 grams of iron oxide reacts with 85.8 grams of carbon monoxide, and the balance equation is shown. So they give us our balanced equation. First thing that they're asking, so right now we're just going to be asked, find the limiting reactant. So with limiting reactants, as I said, you're always going to go from grams of each reactant. So we have 2 reactants, so we're going to do this process twice. If you had 3 reactants, you would do this process 3 times, unfortunately. So now what we're going to do is we're going to convert grams of each reactant to grams of product. Something I want to note, you have 2 products here, right? It doesn't matter, okay? It doesn't matter which product you decide to go to if they don't specify. So a lot of times some teachers will specify and they'll say, figure out how many grams are of product, let's say of iron, are actually produced. And then you have to go to iron. If they're just asking for the limiting reactant, then it doesn't matter which product you decide to go to, since there's 2 of them. And sometimes there might be 3 of them, okay? So it doesn't matter. They're both going to give you the same limiting reactant. Okay. So I'm going to start off with our first reactant, and we're going to go from grams of reactant to grams of product. And what we'll do, our plan overall is going to be going from grams of iron oxide. Then we're going to convert that to moles, because if you aren't sure where to convert it to, go to moles, since everything equals moles. So we're converting this to moles of iron oxide. Now we want to change the compound here. So since we want to change the compound from going from our reactant now to product, and I believe I chose iron, now what we're going to do instead, and actually let me set this up real quick. So setting this up real quick, we started off with 167 grams of iron oxide. That's what was given to us. And I'm going to multiply that by, and on the bottom, I'm going to put the molar mass of iron oxide, which I already did for you guys to save some time. But remember, just finding molar mass, how that was all indicated, it was just figuring out the sum of every single individual element and adding them all together, essentially, is what the sum is saying, right? So that's what we would put here. That's our first conversion factor. Okay, so then next, we're going to get to moles of our product, which I'm picking iron in this case. Like I said, doesn't matter if you chose CO2, both of them are fine. And then I'll use a mole to mole ratio. And that mole to mole ratio that I'm taking this from is based on the balance equation that was given. So we'll see that we have 2 moles right here, 2 moles of iron per every 1 mole. Even if it's not stated, assume there's a 1 if there's no coefficient in front, okay? And then, so there's only 1 mole of iron oxide. And let's cancel things out. So our grams of iron oxide would cancel. Moles of iron oxide would also cancel. And we're at moles of iron. Okay, almost there. So we want to get to grams now. So going from grams, we'll see we're going to grams of iron. And all I need is the molar mass to figure out how many grams of iron there is. I'll set that up and multiply straight across, divide, so multiply straight across, and divide by this value, and we would have gotten grams of iron. We're going to do this exact concept, okay? So we're going to do this exact concept and sort of like process really for the second reactant, which was carbon monoxide, okay? And then at the end for limiting reactants, what we'll see is whatever reactant produces the least amount of product, that's your limiting reactant because your amount of product is limited, right? So that's essentially the concept there. So let's do this process one more time. Okay, so now we'll do everything going from grams of carbon monoxide to grams of iron. So we're going from grams of carbon monoxide, I'll start there, and we're going to figure out and go to moles of carbon monoxide. That's the same process, right? And then we'll use the molar mass of carbon monoxide. We'll use our mole to mole ratio from our balanced equation. And if you guys can see it, it's actually right here. So all of this, let's see, 2 moles, there we go, and 3 moles of carbon monoxide. That's where I found that here. We're canceling everything out accordingly. And that last step, we're trying to get to grams of iron. So grams of iron would be just the molar mass of iron. And then lastly, we would multiply straight across and divide by these 2 multiplied, and we get this value. I think I just had something, Becca said, multiply straight across, more like, I like that. Yes. I like that. That was really cute. Okay. And then what we're going to do at the end is looking at our limiting reactant. We're going to try to figure out which one produced the least amount of product. Okay. So here we'll see we have for iron oxide that produced 116.8 grams of iron, and then carbon monoxide is 114.1 grams of iron. We're looking for the one that produced the least amount of product, which was carbon monoxide. So that produced the least amount, meaning that must be our limiting reactant. And that's the process you would take for every single limiting reactant. Now, the reason why I like to take this step and go from grams to grams of product is because a lot of times these questions then ask you for the theoretical yield. And I actually just found the theoretical yield already. So the theoretical yield is whatever your limiting reactant produces. So this is our theoretical yield. This is not. That doesn't actually get produced. So whatever your limiting reactant produces is your theoretical yield, and that will help you with limiting reactants. Let me see what the questions I've gotten overall, because I covered all the topics. As I take a sip of water. Let's see. Ryan said, if we could go over on how to find the amount of excess left over using the before, change, and after diagram, that would be great. Sure. So I do it a tiny bit differently instead of the BCA diagram. I'll show you what I do for finding the excess. I don't know, I've always preferred it, but I can still show you the before, change, and after. The leftover amount. Okay, so let's do that actually for this one. And I believe I put a blank pages at the end. Let me just write how much we had. Okay, so let's go back. What we're always going to start off with, we found the limiting reactant. That's going to be your first step. Then the next step is to figure out your theoretical yield. So we did that already, right? We stated that our limiting reactant produces, whatever our limiting reactant produces is our theoretical yield. So our theoretical yield is 114.1. Okay. So I'll start off there. You're always going to start off, and I'm going to call this Theo, but you're always going to start off with your theoretical yield. Okay. All right. So Krista Joy just said, I have only ever used the leftover amount Melissa's way. Thank you. I appreciate that, guys. I just prefer it that way. I don't know. I've seen a lot of different tables, and I feel like the tables always confuse me, and they confuse my students. And I'm like, there's no need for extra tables. So, just using the typical stoichiometry way, you guys are always going to see that, and that will always work. So, okay, you're going to start with your theoretical yield that your limiting reactant produced, which we said was 114.1 grams of iron. So that's what we produced. And what we're trying to get to, what we're trying to do is we're going to go from grams of our product, which, as I mentioned, was the theoretical yield. So that's iron in this case. And then we're going to go to moles. So once again, if you're not sure where to go to moles. So we're going to go to moles of iron, and then next we're going to get to moles of our excess reactant. So our excess reactant was the one that is left over, or is the one that it was the iron oxide, I believe. That's what I stated before. Yeah. This is 3 and this is 2. Okay. The iron oxide. And then lastly, we'll have grams of our iron oxide. Okay. That's the overall process. And then Ryan, I'll see what I can do with the tables. It's required for your tests. I'll see what I can do for the BCA tables afterwards. I'll show you this method as well. Okay. So let's start off with converting this to moles. So we said, and let me actually pull up, because I don't have everything on here already. Let me grab the molar mass and everything. Okay, so we found previously that our molar mass of iron was 55.85 grams of iron per every 1 mole of iron. All right, that's this first step. Then next, we're going to do a mole-to-mole ratio. And our mole-to-mole ratio, this was going back to our balanced equation that we found previously, or were given previously. We're going to go from moles of iron on the bottom, and I'm just looking at the balanced equation we had before, and that was 2 moles of iron per every, let's see how many moles of iron oxide. There was 1. Okay. And then lastly, I'm just going to multiply by the actual molar mass of iron oxide, which I found previously, which was 159.7, and then 1 mole on the bottom. All right, running out of room. But that's going to give us how much is actually used. So this whole process of going from the theoretical yield to the actual excess, so this goes from the theoretical yield all the way to the mass of our excess. That's the process here. This just tells us how much is actually used in the reaction. So let me multiply everything out and see what we get. And then we'll figure out how much excess we actually have. Let me do this one more time. Times 2. Okay, so this would have been how much is used is 163.1 grams of iron oxide. That's how much is used. And we would go back to the very beginning and we'd see the original question where it says we're given 167 grams. So this is our original. To figure out our excess amount, we just subtract the amount that we just found that was used, right? So then I'll subtract everything, and that will give us our grams of our excess or our leftover. So subtracting everything, minus 163.1, this gives us 3.9 grams of our excess reactant. Okay, so that would have been how I would approach this question. Let me see what I can do with the BCA table. I'm not too familiar with it, just because I actually didn't even learn it that way back in college. But let me see if I can pull that up. BCA tables are before, change, and after for people who aren't familiar with that. Let me see for excess reactant. You typically see that, and actually, yeah, I typically see that in Chemistry 2, General Chemistry 2, but it makes sense that it's in AP now. So let's see. Just want to see the image of it. Okay, I'm good. So here, let me go to the next part. I'll show you how to use the before, change, and after table. So like I said before, change and after. I'll write just our balanced equation on top. So that's how we typically use something like that. Let me get to our balanced equation again. Okay, so our balanced equation would be here. Let me just write that out. 2Fe plus 3CO2. So we always place our balanced equation on top, and then on the bottom, we'll place the initial amounts. So our initial amount that was given was 100, and so before, so that's what that means, right? Before means initial or given, so that's 167 grams. Carbon monoxide was initially 85.8 grams, okay? And then next, we don't know how much product we produced. So that's going to be something that to note is whenever you have before, we never know how much product is actually produced because that's the after part. So yeah, that should make some more sense there. Now our change, let's go into what you guys are showing for change. Yeah, so our change is going to be based on the coefficients in front, okay? So in this case, there's only one coefficient. There's a one coefficient here, okay? And that's what I'm looking at. So since there's a one coefficient, on your reactant side, it's always going to be subtracting or negative. So it's going to be a negative x. And the reason for that is because reactants are being used up while products are being produced. So that's why those are positive. So in this case, I'm still going to keep going with now the 3 carbon monoxide. And this 3 is actually going to be a negative 3x. So whatever coefficient is in front of that molecular compound that we're looking at, that's where that's going to go. It's going to go with the change with the x. And then next, we'll see, okay, now with iron, this is going to be positive. So plus 2x because it's being produced. So negative on the left, positive on the right. And then now, lastly here, this would have been plus 3x. Okay, I hope that's making some more sense. And then lastly, all you have to do, and by the way, this is a 0 and 0 since we don't know how much that is. All we have to do to find the after is add everything up. So you're combining those two together. So this would have been 167 minus x. This would have been 85.8 minus 3x, and this is just 2x and just 3x. Okay, so that's how you would use a before, change, and after. Now, what you would actually do, you need to solve for x. So solving for x, this is kind of more of, it's not as stoichiometry based, but that's okay. What you would do is we would first find the limiting reactant, as we did before. And since we found the limiting reactant, we would find the limiting reactant first, then we would find how much of our mass is actually produced. That's what I wanted to say. So we'd find how much our actual mass is produced. And what we found before was that 114.1. Now, because this is the amount of grams that we found previously, right, from whatever our limiting reactant produced or theoretical yield, then I could figure out what x is. And that's going to help me figure out then what the excess amount is. I hope you're with me so far. Let me know if that makes some sense as to what I'm saying, okay? So we found the theoretical yield that we still needed. What I'm going to do next is I'm actually just going to solve for x. And how I can do this is by stating 2x is equal to that theoretical yield, okay? And then just divide by 2. That's going to help me solve for x. So let's see what that would have given us. And that would have been, let me make some room. 57 here. X is equal to 57.05. All right. So it would give us that amount. And then from there, you would just plug in. So that would help you identify here. 0.05. Actually, that doesn't even give us what we wanted. Let me see how you guys are doing it, because I know it's totally different. That's how you use the table. I'm not usually using this table for that. But you do have to find the change, and you would subtract and add everything up, and that would give you the end result. And that should have worked. Let me make sure. I'm surprised they make you use it this way. Yeah, I'm surprised they make you use it this way. I'm not a fan of it either. Oh, that's why. That's right. That's right. One key thing, and that was my bad. Sorry about that. The moles. We always want it in moles before changing after. So make sure to always have everything converted to moles already. So the setup is correct. However, this should have been converted to moles of iron oxide. That's right. Before, change, and after. You're going to see this in the second half of chemistry as well. Yeah. And then that would be here. Okay. Whatever moles amount that would be. And then it would work. So that's the concept behind it, Ryan. Okay, cool. I'm glad it makes sense. Yeah. Sorry about that. Yeah. It's moles. And I think actually, yeah, we covered everything else. That's pretty much it. I wanted to mention how this is going to work, how this live show is now going to be. So if you would like the chance for me to answer your questions and actually turn them into a detailed lesson based on your question, please tweet me. So how this is going to be is you can tweet me your questions on my Twitter at HelloMelissaM. And then make sure to use the hashtag AskMelissaMaribel. And there I'll see all the different chemistry questions that you guys are giving me. All the different questions you guys are giving me throughout the week. And please send those to me before Sunday, before my next live, because that allows me some time to create an actual lesson for you guys, since it makes it just so much easier to do. Okay, so I highly recommend, please tweet me your questions. If you have questions throughout the week, by all means, tweet me throughout the entire week. And then at the next live, next Sunday, I will answer a select amount, and I will turn those into a detailed lesson. So does that make sense, guys? Is that we okay with that? Understanding that? I think people are asking a couple questions here. Let me see what else we had. Krista said, my professor does it non-algebraically. It's in grams of reactants and products and subtracted on the reactants, then the final is calculated dependent on the limiting reactant, which I guess is the same concept. It is the same concept. Yeah, everyone tends to do this differently for some reason. I always preferred the stoichiometry way just because you guys need to know stoichiometry. So I'd rather you be familiar with the process instead of a before, change, and after, because you don't use that often. So I understand that maybe they like to see the visuals, but once you understand stoichiometry, it's just easier, I feel. But yeah, those are just different ways. Becca just said, I've never tried the before, change, and after table, but it seems like a cool way to keep everything organized. It is. It definitely is. Like there's so many different ways. I think someone from a completely different country told me there's another like algebraic way. It's kind of like when I looked at it first, I was just like, there's no need to do it that way. But then I realized that it like skips balancing equations. It was insane, but it's really cool to just see how many different ways you can do these things. And of course, I'm always willing to see if there's other ways, but this is just what worked for myself and for my students. And then, so Clitsy just said, totally enjoyed the lesson. Thank you. Everything makes sense now. Thank you, Melissa. You're so welcome. So I'm so glad that this makes so much more sense. Krista said, thank you so much for the study session and answering my Twitter question. Absolutely. So yeah. And then Ryan said, thank you. Happy Labor Day. Sleep in day. Yes. Extra procrastination time. Well then, I think we all know what you're doing. So I hope you guys have a great, happy Labor Day weekend as well. So by the way, everyone who's, leaving after this live stream or going to watch the replay later on, I highly recommend checking the description box because I will have all the timestamps there. And I also have several helpful resources in the description box. So I have, from chemistry guides to notes to other resources that I personally use throughout college. Highly recommend them. And I'm always trying to find a way to make things easier because I was a chemistry major and I had plenty on my plate. Okay, so I totally understand what it's like and going through even being in AP classes in high school. So I was definitely that person as well. So, all right, guys, tweet me throughout the week your questions on Twitter, and I will see you in the next live. Thank you so much for joining me, and I hope you enjoy your long weekend. See you guys.